Right, we're almost done with this semester, guys. I promise. I'd like you to take a look at this video where I kind of give you a very, very brief introduction into one of the big things we're going to do in calculus next year. I know not everybody has signed up for calculus next year, so just bear with us. This is nothing that you can't handle. And it's kind of cool to know where we're headed after all of this just, algebra and trigonometry work that we've done so far. All right, so one of the things we work on in calculus is figuring out an instantaneous rate of change. So if we had a line, we could figure out the slope by just figuring out the change in y over the change in x. So taking y2 minus y1, dividing it by x2 minus x1. So slope, if you have a straight line or something that doesn't have a variable slope or a variable rate of change, you just use the slope formula. It's the ratio of the change in y to change in x, or change in horizontal movement versus vertical movement, where you've got vertical on top and horizontal on the bottom. All right, but as you can see on this, what would be a cubic graph of some sort, your slopes are going to be all different as you move through this graph. So at the light blue point, I don't know, our slope would be, kind of doing something like that. At this purple dot, it seems to be maybe kind of more, I don't know, maybe down 2 over 1, something like that. And then here at this green dot, the slope seems to also be pretty steep, but it's hard to tell exactly what it is because, we don't have another point relative to that point that's going to be, at the same rate of change. All right, so in calculus, we look at the instantaneous rate of change, which is just the slope of a curve at any given point. And you know what that is? It's a limit. So when you're finding the limit, what you're technically doing is finding what's that instantaneous rate of change. So for a function to be continuous, and this is something that you worked on yesterday on that Desmos activity, for a function to be continuous, you have to be approaching the same value as you move from left and from the right to that point. Also, you can't have a discontinuity there. You can't be reaching the same point, but then have a dot down here and just a hole here. The definition of continuity is that the left-hand limit and the right-hand limit equal the function value at any given point. So for a function to be continuous, then the left and the right limits must equal the function value. Now, why are we talking about continuity right now? Well, you can only find the instantaneous rate of change if a function is continuous. And that's one of the first things that we work on in calculus is proving that a function is continuous and how we do that. And we do that like you've been doing the last couple of days, where you think about what are you reaching as you move from the left to that point, and what are you approaching as you move from the right to that point? And then is it continuous there? Or is the function, is there a point somewhere above or below where you're reaching? That's a dot that would represent the function value. So you need to have left and right hand limits equaling the function value. All right, so how do you find the limit though if you don't have a graph? Well, very rarely will you actually have access to a graph. Instead, you're going to have some sort of a function, especially a function that relates to something with an economic context or something maybe with a physics context. Not everything can be graphed easily by hand. So what we can do is just use direct substitution and algebra. Yay, us! So here, this first example up at the top says find the limit as x approaches 2 of the function f of x equals x. All right, so all we're going to do is take what we're trying to approach to, and we're going to plug it in right here. And so 2 is equal to 2. So the limit of whatever this function is as x approaches 2 is equal to 2. Now, if you think about what function family does that belong to? It belongs to the linear function family. It's going to cross through the y-axis at 0, and it's going to have a slope of up 1 over 1 because the slope is like a 1. So go up 1 over 1, up 1 over 1 again, and what's the limit, or what's that? What is the point approaching as you move from the left into the right? And from the right, well, you're approaching 2. All right, so this next example, I couldn't tell you anything about what this graph is going to look like. I do know that it will have a few vertical asymptotes. It will have 2 vertical asymptotes, I think. Well, maybe not. I know for sure it's going to have a vertical asymptote because there's a value that I could plug in here to get a 0 in the denominator. We can't divide by 0. That's where you get vertical asymptotes. All right, so anyway, I don't know what the graph looks like, so I can't estimate what the function's approaching as you move from the left to the point and from the right to the point. as I'm moving toward one being the point. So instead, I think, can I do some algebra? And the first thing I recognize is that this denominator, I could factor out an x. I'm left with a quantity x plus 2. Hallelujah! X plus 2's cancel, and then this function just boils down to negative 1 over x. Now it's time for that direct substitution. If I plug in a 1 right here, negative 1 divided by 1 is negative 1. So I would say that the limit as x approaches 1 of this function is equal to negative 1. So I wish I could have written them on my screen, but I can't really do that on my Chromebook. So anywho, remember direct substitution, the limit of this first expression would just be 2. Of this second expression, you do some algebra to clean it up, and then just plug in 1. And the limit as x approaches 1 of this function would be equal to negative 1. All right, and then I have a real treat for us. Let's find the limit as x approaches 2 pi over 3 of the function negative secant of 2x. Oh, so many wonderful memories in this problem. So here's my thought bubble. And in calculus, this is what I'm going to have you do a lot of the time. I'm going to have you, first of all, start by writing down your thoughts. These are my thoughts that came to mind. Well, I know that secant is the reciprocal of cosine. So it's like 1 over cosine. What's cosine? SOHCAHTOA. Cosine, adjacent over hypotenuse. All right, 2 pi over 3, well, that's a 60-degree angle because when I take 180 divided by 3, that's a 60-degreeer. 2 pi over 3 would be here in my second quadrant. So the reference angle of 60 degrees in the second quadrant. Oh yes, remember that cosine is negative in the second quadrant. So this is a negative 1, and that's a square root of 3, and that's a 2. The hypotenuse is 2. So that's 2 pi over 3, on my unit circle. So hopefully all of those thoughts mean something to you, and you can come up with those thoughts just as quickly as I did. All right, let's get down to business. Let's find the limit as x approaches 2 pi over 3 of this function. So I plug in 2 pi over 3 for x, direct substitution. That gives me 4 pi over 3. Well, wait a minute. Where's 4 pi over 3? Oh, I forgot my thought bubble, but it's there. All right, I had 1 pi over 3, 2 pi over 3, 3 over 3 pi is just pi. 4 pi over 3 is down here in quadrant 3 where everything's negative. Well, nope, timeout. Only cosine and sine are negative. Tangent will be positive. All right, so 4 pi over 3 is down here. I am really old and I've been doing this a really long time, and I still draw that unit circle. Do it, people. All right, so here's my little quadrant 3 of that unit circle. 4 pi over 3 is my angle, 60-degree reference angle. Now, let's just evaluate. So I've got negative 1 over the cosine of 4 pi over 3. Well, the cosine of 4 pi over 3 would be negative 1 over 2, adjacent over hypotenuse. So negative 1 over negative 1/2, skip, flip, multiply. So I canceled out my negatives, and then I multiplied by the reciprocal of 1/2, which is 2, and that gives me just 2. So what is the limit as x approaches 2 pi over 3 of this function? The limit is 2. You don't believe me? Well, guess what? I can prove it to you graphically. Hey, I remember this graph. This is the graph of cosine, or secant, I mean. Cosine would be like, starting at 1 and then bottoming out here at pi over 2, coming back at pi, going up, ending at 2 pi, or something like that. Okay, so can you imagine the cosine graph drawn in here? I can. So secant, we just, draw asymptotes everywhere we had a 0 because you can't divide by 0, and then you flip it over. It's like you fillet that cosine graph. All right, so remember, what were we even talking about? Oh my goodness. Oh, we wanted to find what's the function approaching at 2 pi over 3. So real quick, I went into my calculator. That was me opening up my calculator. And I said to myself, what is 2 pi over 3? Well, 2 times 3.14 divided by 3 gave me 2.09. So really it's like, what is this function approaching as x gets really close to 2.09 in decimal form? Okay, so here we are. Here's 2, a little bit past 2 would be like that, 2.09. Check it out. The function is approaching 2. So as I move from the left to that point, 2.09, I have an output of 2. As I move from the right to that 2.09, I also approach 2. Cool So I can prove it to you graphically as well. Now, could you have graphed that quickly and easily? Not quickly. You probably could have done it pretty easily. And is it really, worth your time and effort to graph that? No. We need these others. We need these other techniques. We need our trig. We need direct substitution. And of course, we need our brains most importantly. All right, so that's all I have to say about finding a limit using direct substitution and algebra. In the Google Classroom, I have a worksheet for you. I would like you to work through it and come up with your answers. And that's all I have to say about that. All right, talk to you later.